jazz up what I do for a job, nice introduction. But to be honest with you, a lot of what I spend my time talking about, really, when we get down to it, is about boxes and arrows. And that's that. Look, we can sugarcoat it all we want. This is a large part of what I do with my clients. I help them with, architecture and strategy and all these lovely things. But it comes down to boxes and arrows. And sometimes we're talking about, well, how big those boxes should be, or maybe, more importantly for some of you, how small those boxes should be. Deeply important conversations like that. More important conversations we often have involve things like, well, what should be in the boxes? And maybe we should break those boxes up into smaller boxes. Yes, you probably should do that as well. But even more important than that, of course, we can have conversations about what shape the boxes should be. And of course, I've made my choice. I am very much on board with Team Hexagon. This also, bits of little advertising, because there's hexagons all over the cover of my book. Please buy my book. I have a mortgage to pay for. So today, though, we're not really going to be talking about the boxes that much. We're actually going to be talking about the other important constituent of my job, the arrows between them. What are these arrows and what do they represent? This is not a talk specifically about microservices. But this is a talk that's been influenced by my work in that space. Fundamentally here, we're talking about any kind of distributed system and the way in which we communicate between it, but any kind of general service architecture. And when I draw a diagram with a service architecture, I think it's important to be clear. This is a talk all about clarity and meaning. So I think it's important that I am clear about what I draw an arrow and what the direction means. Sometimes people use arrows to denote things like data flow. And it's like, that makes no sense to me because data normally flows in two directions anyway. It's not like I send no data and then data magically appears. For me, the arrows that I draw are much simpler than this. They are referring to some form of dependency. In any services-based architecture, whether you think it's micro or not, our systems exist because of relationships and dependencies between these services. So an arrow here from the returns microservice to the shipping microservice, what that is showing is a logical dependency. The returns microservice depends on functionality that shipping provides. And often in this context, we'll talk about the thing on the left of the arrow, the returns microservice here being the consumer. I am consuming functionality that the shipping microservice provides. So this talk really is about trying to explore some of the different ways in which this communication can happen. How do we implement these dependencies? And specifically, what the hell is the difference between synchronous and asynchronous communication? Because it turns out there isn't one. But we'll get to that a bit later. There are other distinctions I like to use when describing service-based communication that I think are a bit more crystal and a bit more clear. They may be operating more at the logical level. When we start getting into conversations about synchronous versus asynchronous communication, we're starting to get into implementation detail, and I think it's often useful to start talking about the nature of the interactions first. And in that context, excuse me, the distinction I've found to be most useful is the difference between request-response-oriented communication and event-driven communication. So request-response, I think both of these are pretty clear-cut styles of integration. Request-response is probably the most common, it's the most familiar to many of you. This is where we sort of almost, it maps the mental model of treating a service like a big object that you call methods on, which is absolutely correct and also completely wrong at the same time, but it does at least fit that model, right? Here in this context here, the returns microservice wants to achieve something, it needs to do something, it needs to carry out some kind of job. How does it carry out that job? It sends a request. Please, can you help me? I need help. You can help me. So you send a request. I prefer the term request. Some people use the word command. I prefer request because it's a bit softer. Command implies something which must be obeyed. And actually, it is completely valid, even in a completely functioning system, for sometimes these requests to be rejected. For example, you might be asking for an invalid state transition. That can happen, and it's okay for you to say no. So that's why I call them a request. I prefer this language. It's also the language we use in the HTTP specification, which tends to be the protocol that most of us end up using. So here I'm saying I need a postage label, and I'm going to consume the response. Hopefully in this situation, I'm going to get a response. The response comes back and says, here you go, here's your postage label. Nice, straightforward, tends to be one thing talking to one other thing. And you can implement this in a variety of different ways. And we're going to look mostly at different ways of implementing this interaction in the context of what asynchronous means. Event-driven interactions are quite different and they can break people's brains, but this is my own preferred natural style of integration. Rather than telling anybody to do something, we're merely talking about events being emitted and things reacting to events. So in this situation here, the inventory microservice is saying, we've just received a large amount of stock. So we've put out an event that says we've just received 10,000 copies of Justin Bieber's greatest hits. And we're alerting you to this fact so you can get out of the building or whatever it is you need to do. You can think of an event-driven system as like with an event, you put the event on a notice board and then you walk away, and it is up to other people what they decide to do with that information. So in this particular scenario, we've got both promotions and wishlist microservices, and they are going to do completely different things with that same event. The promotions microservice is going to say, well, look, my job is to automatically discount products. So at certain thresholds of inventory, I might take, say, 5%, 10% off the recommended retail price. So we've got a lot of Justin Bieber. Hell, we're going to get rid of the Justin Bieber. Let's discount. That same event will trigger different behavior in the wishlist service, which is tracking, in this example, all of you believers out there that said, please let me know when you've got more Biebs in. So we've told the wishlist microservice, new Biebs is available, and it can go, does anyone want this? Yes, let's email them and let them know. One event causing different things to happen. And in this context, we would talk about the things on the right side being the consumers. They are receiving that information, now consuming that information. They're sort of dependent on the event, so arguably these arrows can go one or two ways. At a certain point, the arrow direction starts getting quite fuzzy with event-driven systems. We're mostly not going to be talking about event-driven architectures today because I think you naturally fall into a certain style of implementation with these styles of architecture. What we're mostly going to be talking about today is this. Synchronous versus asynchronous. What does it mean? Now, in the past, I would sort of try and map these terms together. I would talk about the fact that request response could be synchronous or asynchronous, but that event-driven architecture is always inherently asynchronous. And as we'll see when we go through, this is probably still true, although what that word asynchronous means varies greatly, to the point where even if we look at asynchronous, the word asynchronous, just in the context of service-to-service-based communication, there are so many conflicting definitions that this term is essentially meaningless, useless, and confusing, and is also widely used. I was inspired to write this talk by this blog post by Pat Helland. It's on his sublist, but you get the idea. It's blogs, but with email. Pat Helland, one of the pioneers of computing, wrote this article where he posited the hypothesis, well, not the hypothesis, he posited the idea that the term eventually consistent is not a useful term because, as he rightly points out, we use the term consistency in lots of different contexts in computing to mean very different things, and they're all quite close to the same places where we're having conversations around eventual consistency. If you want to kind of understand what he's getting at, think about an ACID transaction. The C in an ACID transaction stands for consistency. Go and look up what that actually means, because you will be surprised, because it probably has nothing to do with what you think it means. It's a very specific meaning. He was arguing in this article that we should be referring to it as eventually convergent systems, because eventually the replicas in an eventually consistent system will converge on having the same view once they've processed all the messages. It's probably a better term. I want to say right now that this inspired me to write this talk in the hope that I could come up with a better term than asynchronous. I believe in open and honest communication. I have failed. But I at least want to take you through where I'm currently at with this whole process. So this was many years ago now. This was, deep in the midst of still being trapped in my in southeast of England, not going anywhere. And I don't think asynchronous means anything. I put this out on Twitter, and I was like, well, has someone out there got a good definition of what asynchronous means? And, nowadays saying that I got some shocking responses on Twitter, no one would be surprised. But back then, it was still, So I got a whole bunch of really interesting responses, a bunch of them from people I actually knew. And it was kind of interesting because for some of these people, I'd worked with them, and I got very, very different views from a lot of people. So Darren Hobbs was one of the first people that came back, an ex-colleague of mine, and he said that for him, asynchronous communication is sort of comparing asynchronous, asynchronous communication is like sending an email rather than having a phone call. And there's sort of something there that kind of seems interesting, right? But it does sort of imply a speed issue. When I pick up the phone call's immediate, email takes longer. So this sort of implies that asynchronous communication will somehow be slower, which isn't true, actually. And the majority of I think all the low latency systems I've ever worked on have been using various different forms of asynchronous network-based communication. However, there's something interesting here, right? There is something around this interaction. I mean, certainly, of course, we've got the idea that a phone call tends to be from one person to one other person, point to point. Email has the option of there being multiple recipients. So is there something there, maybe? So while this Twitter thread is going on, of course, I started thinking, okay, well, where else do we see smart people writing down their thoughts? And can I look at those thoughts and tear them apart for the benefit of a conference talk? And of course, it's quite easy to do that because we've got things like the Reactive Manifesto, right? So the Reactive Manifesto, hands up who's read the Reactive Manifesto? Hands up who understands the Reactive Manifesto? Some of you put your hands down, that's rude. Now this is written, I know a bunch of people that wrote this. I consider some of them friends. They've made an attempt here to put forward a dogmatic view about how we should do basically distributed system coordination. There's stuff in here I agree with, there's stuff in here I don't agree with. They put a lot of hard work into this, so I want to say all of that up front before I rip it apart for fun. There's a bit in this where they do try and distinguish terms and terminology to try and be precise. The early edition, the first version of the Reactive Manifesto was very different and was kind of very hard to understand. So they've attempted to come back and clarify that. That work was done about 2014. So they actually take an attempt to define what asynchronous means. So I'm thinking, great, smart people thinking about this for a long time, they would have come up with a definition for asynchronous that absolutely resonates with all of us. So here we go, here's asynchronous. Let's look at the highlighted part. We'll come back to the bits later. So for them, asynchronous communication means in the context of this manifesto, we mean that the processing of a request occurs at an arbitrary point in time, sometime after it has been transmitted from client to server. The processing of a request occurs at an arbitrary time, sometime after it has been transmitted from client to server. One more time, the processing of a request occurs at an arbitrary time, sometime after it's been transmitted. Would this be as opposed to processing the request before it's been sent? Like with some kind of crazy time warp hole shenanigans or something? Or this makes no sense, right? Because we know causality is a thing, even if time dilation exists, causality is very much a thing. We are always going to process a request after it was sent. Otherwise, the world does not work, right? So this is kind of meaningless. But we look elsewhere, and there are other parts where we start getting closer, at least to what the spirit, I think, of the Reactive Manifesto was from some of the people that wrote it anyway. I have spoken to some of the authors who don't agree with each other, but there we are, that's life. We get into this then talking about the comparison now with synchronous communication. So they then say this is the opposite of synchronous processing that implies that the client only resumes its own execution once the service has processed the request. So that's much more precise, but we have a very specific term for this, and it's not asynchronous. We'll come back to that in just a moment. So the thread's still going on. Here's my friend Steve Smith, works at Equal Experts, knows lots about continuous delivery, very nice man. And he said, initially his first response to when I put that tweet out was, well, for him, it's about a TCP connection being open for the duration of communication. So I'm opening a TCP connection, we're talking, and until that communication has ceased, and then I'll close the connection. And of course, I like poking Steve and saying, well, what does that mean if I use a different networking protocol, this all changes? And he said, well, actually, what he actually meant is, I'm assuming you're not blocking for a response. So this is the more precise language we're looking for. This is much more explicit. Non-blocking So that's what this is about, non-blocking. Let's talk about what non-blocking is, because I think this is a much more useful thing to talk about, and it's much more explicit. So let's take a look at an example of an interaction. We've got a microservice here, we've got the enrollment microservice. We can imagine this is a little small orchestrated process. And we're trying to carry out some activities. So one of the things we need to do is to award some points for a customer for doing something. So they give you some points, right? And we also want to upgrade your subscription. So these are two activities, and in this particular implementation, they're done one after the other. Now, in this example, they don't have to be, but that's just how we've implemented it, right? We have a line of code where we send the first request, and then we have a line of code where we send the second request, right? Now, if we implemented these as simple HTTP calls, what would happen is that we would do the first call, we would block and wait until we get the response. And then we would do the second call. And we'd block and wait until we get the response. So we're doing these things sequentially. So one of the challenges, of course, of the blocking call like this is that we've denied ourselves the opportunity to do work in parallel. So in this particular situation, the latency of these operations is now going to be the sum of the calls, whereas actually, by looking at the code, these things could be done in parallel. So if award points takes 50 milliseconds, upgrading subscription takes 150 milliseconds, we're looking at a constraint around our total duration being at least 200 millis. So, well, that's not great, right? And of course, there's the added complexity here, which is that latency has a deviation. And so if you've got lots of different calls happening with different deviations and you multiply them all up together, you'll get a much larger distribution of latency, which in turn makes your system slightly less harder to understand because, anyway, there's different things there. But an obvious improvement, not only in terms, would just be to reduce that latency by doing these two calls in parallel. And so rather than doing this, then this, let's actually just say, well, no, we want to do them both like this. Now, that's actually quite easy to do nowadays. 10 years ago, I would probably have to write some of my own syntactic sugar and probably end up deadlocking my Java code because I don't know how to use a semaphore. Nowadays, I can just use something like a reactive extension for the programming language of my choice. So in this example here, what we've done is we've wrapped that execution in a future. So a future is a read-only type, the value of which is available once the pending operation has completed. So you could assume whatever language I'm using here has got some syntactic sugar where the content of that parentheses is basically being dispatched on a background thread. Could be a green thread, could be a native thread, we don't really care too much. So when I execute that line of code, it immediately returns, and that FUT1 becomes a pointer to the pending operation. But the key thing is that line of code executes, the next line of code executes, we're not blocking and waiting. The calls are now being made in parallel. We're bringing down our latency. This obviously seems like a good idea. These two calls are not causally linked. Therefore, we should be able to do them in parallel. I'm not trying to get the result of one to pass into the second one, for example. So parallelizing these things just makes sense. So now we've got non-blocking clients. The heavens have opened. The Reactive Manifesto has blessed us. You are now reactive, right? But are we? Are we? Because we actually do need the answers, don't we? When we make a call, I'm not blocking and waiting, but why did you make the call? Oh, because I wanted something. So you are going to have to wait for that, though, aren't you? Because at this point here, at the end of those two lines of code being executed, at this point in time, it's possible the calls those services have completed, or it's possible they haven't. We actually don't know. And we won't know until we look at the state of the future. If we actually need the information that comes back, we might want clarification that yes, the subscription has been upgraded, and yes, these points have been applied. Maybe to pass back success to the thing that's called our microservice, or to carry out some other operation. So we actually need to wait somewhere. And that's where we'd use something like an await. And what does an await do? It blocks and it waits. And it's all I've seen lots of people say, okay, I've made my code all reactive and it's non-blocking, and it's just async awaits everywhere. And that's fine, but you're blocking and waiting. It's rare, in fact, that you don't end up somewhere in the client code having to actually stop and wait. There's other issues we'll get to around failure modes, which we'll take a look at later on. So the thing is, even if you're doing non-blocking calls, the logic of your processing may require that you still have to wait for things to happen. Ultimately, if you care about a result in an interaction, you're going to have to wait to get the result. If you don't care about it, fine. Not a lot of request-response interactions fall into that. Event-driven stuff does, but we tend to work with that at a different level of abstraction. But the way to think about this is that even non-blocking calls can end up blocking. That said, this is still a good thing to do, because even if we ultimately do end up blocking, the fact that we've been able to do those calls in parallel is still a good thing. So it is still a good idea to do this. Just be aware of the limitations. So we're just getting started, we're just getting warmed up. What other forms of asynchronous are out there? We've got a post here from Graham Lee. Graham Lee worked for many years at Tyro, which is a payments company in Australia. Had sort of this interesting microservice architecture going on. And so Graham came back and he said, well, the definition that I've been using is the sending service doesn't wait for completion of the receiving service's work before continuing and or completing its work. So that first kind of sentence he says there is really non-blocking. What he's talking about there is non-blocking. But he says, well, now though that I think about it, I expect temporal decoupling from the receiving service's availability. Now, temporal decoupling is an interesting term because we actually use, that is a term that we also use in different places in computing to mean very different things. In the context of of service-to-service communication, we're talking about service A needs service B to be there to complete some operation. So then we have Benjamin Johnson saying for him, synchronous communication is direct communication between sender and receiver. Async is there's an intermediary involved between the sender and receiver, for example, the message broker. And it's often these intermediaries that we use to deal with this temporal coupling problem. And the classic type of of an intermediary is, as is mentioned, a message broker. It could be Rabbit, could be ActiveMQ, Kafka, whatever you might want, but some kind of middleware. So the way these intermediaries work is, and there's different versions of it, if I want to get something from A to B, rather than talking directly to B, so if I talk directly to B, B might not be there. For this operation to complete, B needs to be there, needs to be available. That's a temporal coupling issue. So to remove that, we instead deliver the message to the intermediary, and the intermediary ensures that the message can get to the recipient. And so the broker's doing that for us. So in this situation here, I've got my message, I'm putting it in the broker, and then it's the broker's job to make sure that it gets delivered. We have other more dumb intermediaries. You can use a file system like an intermediary, in which case the onus is on the recipient to keep holding a location of a file system, for example. But in this case, the message broker is going to help make sure this thing gets delivered. And the reason we often like message brokers is basically because of that temporal decoupling issue. We are offloading guarantees around delivery to the broker itself. We're not worried as much about client-side issues like retries and things like that, because we're assuming that the message broker itself is a more highly available component than our own services are, and the message broker itself has that logic internally for effectively at a low level doing retries and the like. So once B becomes available, the message will get delivered. So it's sort of offloading that requirement. And I think in software engineering in general, it's always a good idea to offload work to people that are smarter than you, which is normally most people, right? The people that wrote message brokers are going to write a better message broker than me, so I'm going to use their software. That's kind of the way I like to operate. So I had another tweet kind of along these lines. So asynchronous communication for them is like dropping snail mail in a red post box and then getting on with your life. And then boom, one day, Postman Pat stuffs something into your house mailbox along with millions of coupons and charity mailers. Now, some of you might not necessarily be aware of who Postman Pat is. This is the OG Postman Pat. There's apparently a new CG Postman Pat that has a hovergraph. This is the original Postman Pat represent. And he would go around delivering your mail, and he would be relied upon in our metaphor. He is our message broker to an extent. Well, not only he's the kind of delivery mechanism, but the message broker also really, from a metaphorical point of view, is giving us this idea of a mailbox. Okay, so these are quite common, of course, in the US because you can't go onto people's properties because they'll shoot you, so you have to leave the post at the end of the door. So, but nonetheless, this is the idea, right? So you can be away from home, you come back, the letters are there waiting for you, and that's when you pick them up, right? It's a lovely idea. And sort of really what we're talking about here is an intermediary providing some kind of durable inbox, a place where I can put a message. I sort of use the term message as a kind of generic thing that I'm sending over an intermediary, which could encompass a request, a response, or an event. So I give you a message, I put that in that durable store, and it's going to be there for later on. So you can use things like databases as intermediaries. Oracle made millions out doing this. You probably shouldn't do this a lot, right? But for basic things, it's fine. You absolutely can use file systems for this. A large amount of digital systems out there are basically digital recreations of existing paper-based processes. And we've gone from moving bits of paper around to moving files around. Massive banks still operate mostly by passing files around. Here we're using the file system as our intermediary. You can also use email as an intermediary mechanism for communication between services, but don't, because it's a stupid idea. But the fundamental fact of this is, and the benefit of this style of intermediary-based communication, is that the sender of the message does not need to worry about whether or not the client or the recipient is currently available. That's that temporal decoupling issue coming about. We do, of course, though, need to trust the intermediary. So we need to make sure that we've got, if we're using a message broker, a good one. One that is not only good software, but it also that is managed well. Running and managing message brokers isn't necessarily a trivial act. And I've seen lots of situations where people have lost messages in production systems, not through fault of the message broker, but through the fault of the people operating it, not reading how to run a message broker. So let's look at how we might use a message broker for, say, implementing that request-response-based communication we looked at earlier. So in this example here, service A is going to put a request in a message and send that request. And so we've got a queue that B is listening from. So this would be B's queue that effectively is its request queue. So I send the request to the request queue, and then assuming B's available right now, B might get that request straight away. So it's now got the request. Now I'm going to do the processing. I've done the work. I've got my result. So I'm now going to create the response, and I'm going to send it back. And I'd have a separate queue for this. So A will be publishing to the request queue, but listening to the response queue. So I pop something in there, and the result comes back in. Real straightforward and easy, right? This is an example of intermediary-based, request-response-based communication. So pretty easy and clear-cut. It's not, because there's nuance here. When I open a network connection from one process and talk to another machine, the responses come back over that same network connection. But we don't have a single network path between the two of us. We're going via this intermediary. So when that response comes back, it's not coming back over the same network connection necessarily to the same process that opened that network connection in the first place. I've simplified the world at the moment. I've implied there's one A and there's one B. In reality, it's much more likely you'll have multiple copies of A's and multiple instances of B. This is very, very likely to be the case. So when I send that request to B, and B sends back that response, on a lot of message brokers, there would not be any way for me to guarantee that the instance that sent the request is going to get the same response back. So a different instance of A could get that response. And immediately people think, oh, it's a massive problem. That's a real issue. Because I sent that request and I need the response back in my code. So then they start thinking of ways they can make sure that the request kind of gets routed back. They start sharding queues and all this sort of stuff. And I'm like, no, you're solving the wrong problem. What you're basically doing here is you're saying my client code is going to hang around. I'm going to maintain in-memory state to be able to handle the response back in this running node. And I want to route the message so it comes back to the same thing that sent the request. What happens if that node dies? Oh, okay, so if A dies, well, what we'll do is we'll replicate the in-memory state. Now you've got another problem, right? It's much better for you to build your application in such a way that any of the instances of A can process the response that was sent from any of the instances of A. Because that will make your system much easier to scale, and it will make it much more robust. You're not relying on in-memory replication of state. Building stateful systems is a pain in the bum, and you should do absolutely everything you can possibly do to never do that ever. What we're aiming for here is entirely stateless processing of a request or a response. When I get a request, I should be able to get everything I need out of that request to know how to process it correctly. Likewise with a response. How do you solve this? Not most of the time. You stick stuff in a database, and it's fine, right? So I've done something, I've kicked it off, I put some information in a database. When the response comes back in, my instance of A picks it up, says, we've got this. What do I do with this? I get some information from my database, I bring that stuff back together, and away I go. And you can do funky functional stuff with continuations if you want to. That's very, very cool. It hurts people's brains even more, but it does kind of work. Right, so this is good. I actually quite like this. It's a forcing function. This is actually helping us understand and reason about what happens when nodes fail during orchestrated flows like this. We come back to our code from before, our lovely non-blocking code. We've got one bit of code running in one program, right? With our, we're doing a little dispatching, you'll do something, and then you come back. And what happens in this situation? We've got the assumption that everything's coming back to the same instance. So what happens if the code dies halfway through? What happens if this client dies? We've sent those requests out, but we haven't yet processed the results of those requests. And then our node dies. That can happen, right? It's possible. Now, in practice, the way we solve this is just use retry. Make your operations idempotent, and you retry. And it really is that simple. But you have to at least have reasoned about it and make sure it's okay to retry and know the fact that it has died and know the fact that this overarching operation has not completed. It's not as visible to you when you're implementing systems like this. I think it becomes a little bit more obvious when you're sending things like over brokers sometimes because you're having to now think about the routing and then these things come more to the fore. So I think it's arguable that when you're using intermediaries, sort of intermediary-based communication, I think it's arguable that this actually encourages more stateless processing. So what some people see as a problem, I actually see as an opportunity to build better software. So we've got all of these competing definitions out there. We've run just a few of them today already. And there's probably more, there are more out there. I know that for a fact. I've collected a lot more since. There's maybe a question here about immediacy. How quickly do you react to the thing being sent? And the Reactive Manifesto's idea, maybe we're supposed to react to these things before they're sent. We just don't know. We've got temporal coupling, right? If for some people, asynchronous means we avoid temporal coupling. Other people think it's about non-blocking. For others, it's that we have to use some kind of intermediary. Now, all of these things can be useful concepts, but they're all different things. So it's very hard, therefore, to say, what does asynchronous mean? Will the real asynchronous communication please stand up? Now, let's be clear. Let's ask a simple question, right? Does it matter? Well, I hope so, because you've sat through 35 minutes so far, and there's got to be a point to this talk somewhere. But fundamentally, words have different meanings. Many of you here are not speaking English as a first language, and you'll be painfully aware of the fact that words don't have different meanings, because when learning English, it is an annoying language sometimes. Does anyone want to guess for me, bit of audience interaction, this could always go badly, what word in the English language has the most meanings in the Oxford English Dictionary? And then I mean the full Oxford English Dictionary. Does anyone know? Not get, it's very close. Well, it's the opposite. It's what always goes with get? Set. You're so close. It's set in the current edition. I mean, in object-oriented and good object-oriented programming, you always have both of those, right? Now, so we've got set. Set. Now, in the new edition of the full Oxford English Dictionary that's coming out in 2037, that's how long it takes them to come out with the new editions, right? It's going to be run. Set in the current edition has 430 meanings. Right, 430. Oh, run currently has 645. So the last edition with the 430 meanings was the edition that was completed in 1987. So it doesn't get fully reissued very often. This thing is 60 volumes, the full Oxford English Dictionary. So But we are used to this though, right? Now, I'm not going to expect you to know all 430 meanings, but you probably already, as people who might speak English as a second, third or fourth language, you probably already know lots of ways to use the word set. And I don't always have to explain to you how I'm using the word set because you can kind of work it out. We're used to this. Because fundamentally, what we're very good at doing as humans is basically deriving the understanding of words from the context in which that word is used. I had a great conversation with Ian Cooper about this a while ago, and some people have a hinterland. Ian Cooper has like the whole Alps as his hinterland, right? Because obviously it turns out, beyond knowing an awful lot about messaging and distributed systems, he also studied semiotics at university, right? He's explained to me about, this is all about meaning. He said that the meaning of a word becomes more narrow as we put other words around it. This is us adding the context around the word as we communicate to allow the person reading or hearing that word to know what it means. And we don't process it like a computer, it's all instinctual, that's what's going on. So we're going to try a little experiment to see how this works. So I want you to think about what the word run means. You just pick the first definition in your head. Think of run. What does run mean? For some of you, it might mean running. Picture it in your head, right? What does it mean? I'm now going to put some words around run to see if what I was thinking matches your definition. The issue got worse the moment the program was run. Now, it's possible many of you were thinking about jogging or something. I wasn't thinking about jogging. If I just said the word run without any other words, it's hard to know. Now it's become more specific. Let's try again. Think of a different definition or different meaning or different context in which you'd use the word run. Let's go again. This time, this is what I'm thinking about. The economy crashed due to a run on the banks. Two very different contexts. Probably all of you had different versions of run in your head, but it's okay, it's fine, because we put other words around it and the context becomes clear. So does it matter? The issue is we don't put the word asynchronous, then put other words around it to give it meaning. We just use the word asynchronous by itself. We don't give the context. So we can't derive shared meaning from it either. I did keep digging deeper, by the way. I went back to the Reactive Manifesto as well. And they do actually say what the Oxford English Dictionary defines asynchronous as. This is actually what Google says the Oxford English Dictionary defines asynchronous as, by the way, that first sentence. Because if you actually look at the Oxford English Dictionary, and I mean the full one, right, there are multiple definitions of asynchronous in the Oxford English Dictionary. So when I found out about set and I found out about run, I was like, well, maybe there are other definitions of asynchronous in the Oxford English Dictionary, so maybe they've got a great one for computing. So I went to the actual full OED. If you're a British citizen, you can get this free from any library. You can get online access to it for free. Or it helps to have like my brother's a medieval researcher, so he has access to it for some reason. So he looked it up for me. So we looked in, there's lots of different definitions of asynchronous in there, and they talk to you about the context in which these definitions come from. And we find that the definition of asynchronous that the Reactive Manifesto uses, and the majority of the internet uses, is just the first result. And this is specifically a meaning. This is not synchronous, not existing or occurring at the same time, not coinciding in time. That's the Oxford English Dictionary, apparently, definition, singular, of asynchronous. Turns out this definition actually comes from medical contexts. We're working in a medical context? I don't believe we are. So I thought, well, is there actually a computing definition in there? Turns out there is. There's a whole section on computing and asynchronous in the Oxford English Dictionary. And there's actually two separate definitions. And there's one that's more about internal sort of chip behavior. There's one that does actually speak to sort of inter-process communication. I thought, pay dirt. I found it. Great, here we go. So I dug this definition out, and here it is. Designating data transmission in which packets of data are sent at irregular intervals, with the start and end of each packet being marked by specific signals involving such transmission. I don't know what that means. It's probably got to do with the design of sort of network protocols, right? I'd imagine that means a lot to you if you know the ins and outs of things like QUIC and designing your own low-level networking protocols on raw sockets and UDP and everything else. But this is not, although this is still talking about communication, it's talking again about it in a different context to where we talk about communication. The reason I'm getting to all of this is that we have to recognize that software fundamentally is a type of socio-technical system, right? Socio-technical system. What does this mean, right? Socio, people. Human beings being human, right? That's what we are. People. And technology. This is a kind of in the Greek sense of technology, right? So it means a kind of a knowledge-based system. We typically think of it in terms of computers and hardware, but it can mean other things. So at this point, you're thinking, oh God, there's some sort of liberal snowflake that's going to start ramming politics down our throat, talking about how people have just got to get along. Actually, the concept of socio-technical systems was first kind of explored when looking into coal mining during World War II. And this is quite rugged, it's coal mining, right? So for them, the technology involved here was the mining equipment and everything else that was going on. And so they were looking at these systems as a whole to make them safer and understand how they worked. We have to recognize that the amount of software created by individuals is vanishingly rare, the amount of meaningful software created. And a lot of the core celebs for, the hero programmer that did all these stuff by themselves, they didn't do that stuff all by themselves. Linus did the very, very first version of the kernel. It wasn't useful for anybody else. It was hundreds and thousands of people contributing to that made it work. And Linus, for all his faults, made that work, right? People come together to build software. That's what happens. Bringing people together to work on a problem requires good communication. If those people can't work together, it doesn't matter how good the technology is, it's going to fall apart. When you've got two people trying to have a conversation about, we're going to make this asynchronous, and if you've got two very different views of the world, how well is that going to turn out for you? I saw the talk about the Wardley mapping talk before lunch, and a lot of that was taking implicit information and making it explicit, getting it out on the page, visualizing it, helping us see the differences. But the problem when we use a term like asynchronous is a lot of us just have an assumed knowledge about what that word means. And we've got lessons that we've heard before, again and again, about the downsides of communication failing. In the Old Testament, we have the story of the Tower of Babel. It's quite a short story. They talk about how the people of Babel were constructing this glorious tower that was made possible for two reasons. One of which turned out to be new technology and good building materials. It's interesting. That's a fixation of the Old Testament. Right? So lots of. Given that we're having a bit of a crisis about bad concrete in the UK right now, that's especially problematic. Anyway, but the other reason these people were able to come together and build this glorious tower is because they were one people and spoke of one language. Now, the Old Testament God was a fickle character, let's put it that way. And every now and then, he would it was like sort of the late season Game of Thrones characters, where they just changed personality from one episode to the next. And basically, God went, don't like that, and he said they've all got to speak different languages, and the whole thing fell apart. There's no actual rationalization given for that in the Old Testament. There's interpretations to why he did it. But basically, he went and changed all their languages, and they stopped being able to build their glorious tower. So that story's what, only 4,000 years old-ish? Longer than that? We use the term asynchronous, assume everyone knows what it means, but we're not speaking the same term. We're not speaking the same language. So what can we do about this? I don't have a better word that encompasses all the different meanings of asynchronous, and I think that's okay. I think we should use more specific words about what we want. Before you start subscribing to dogma, I've got to be reactive, I've got a t-shirt and everything, it doesn't mean anything. Start by talking about what does our application need? How should our application handle different situations? This is the context in which we're operating. This is what we need for things to work. And then describe how it's going to handle certain situations that any distributed system is going to have to deal with. What should happen when a server is unreachable? How fast do we want the application to be? What should we do if a client crashes? Based on that, you can then describe the nature of the interactions you want and what behaviors you want for those interactions. Use more explicit terms. Say things like clients should use non-blocking calls. Say that you should aim to run operations that can be parallelized in parallel. Talk about using a specific broker as an intermediary and why you're doing it. This will help people understand. Try not to use this, though, as an excuse to go around policing people's language. The title of this talk obviously comes from The Princess Bride, right? And in Guillermo, the whole joke here is Inigo Montoya, along with everybody else in the film and the watchers at home, we all know what inconceivable means. It's Vinicus that's having the problem. This is why the joke kind of works. You keep using that word. I do not think it means what you think it means, as though that there's one universal definition. And in the context of The Princess Bride, there is, of what inconceivable means, but there isn't for us with asynchronous. So maybe the next time someone says to you, we should make this asynchronous, just maybe ask the question, what does that mean to you? Because the answer might shock you. You can find out lots more information at my website. There's things I've done. I've been doing these talks for a long time. I'm getting older. If you watch them all after, you'll see me getting grayer, which is, apparently a thing. But lots more information over at my website. You can also see information about the work that I do with my clients and everything else. But other than that, thank you.